the possible positive sequel to topological recursion?
Thank you for the invitation to talk and the insertion into the title. I'm an optimist, so positive is always a good thing. So I cheated a little bit because somehow my talk got moved up, and I thought I would have time to do slides, but now it's a Blackboard talk, which may be a good thing because I tend to be fast, and then that would make it faster. So I prepared the board a little bit. I'll get to these formulas. Let me just get the overview. So a prequel is before the days of topological recursion. In '96, actually, there is a sequence of papers with Kontsevich Manin, myself, Manin and Zagier, where we actually had this phenomenon by looking at Higher Weil Peterson volumes. We found some recursion formula which kills one puncture. And this was about Higher Weil Peterson volumes, and why these things worked were because they're a logarithmic homological field theory of dimension 1. So this is explained in this paper KMK, and in the paper Kontsevich Manin, the famous one. And there is actually a pairing which we can see between those two things. So this is somehow because you're integrating forms, basically. You're integrating forms over a boundary strata of moduli space. And there are other things like, my handwriting gets bad, so there are more things like the Laplace transform we've seen is also already in that paper, that this makes your coefficients look nicer and you can solve the equations. So this is 96, I guess other people started 2004 or something like this. Then I'll switch gears, so this is quite a jump into the future. So just actually this month a sequence of 2 papers appeared where the title is something about Hopf algebras. And this is something about polylogs. We'll find primitive elements which are related to the logarithmic homological field theories and graphs and so on. And one can take these things and then reconstruct moduli spaces, which I had up here. And then there's something nice about compactifications and master equations, but I think C and D are overzealous. I can't probably not talk about this, but you feel free to ask me afterwards. And then part 3 is kind of free speculation. There are some things where I think there's a more general theory that what we're doing here is a special type of one of these categories sitting here, which is related to just graphs or modular graphs, and you could do it for other things. So simpler things would be trees, and if you do this for trees or even more simpler things like simplices, here in this side you get Goncharov's formula for multi-zeta values, and the same thing for polylogs, which we've heard about today. So I think there's a whole story, and this is why I call it a possible sequel, because this will depend on the category of combinatorial category you're studying. You will get different results, but there is one which actually does reconstruct moduli spaces. All right, so let me get started with the old part. So the old part is old. So this is, maybe I should write this here. This is about Higher Weil Peterson volumes. And I think actually we coined the term. So the previous person that looked at just Weil Peterson volumes was Zograf, and then we studied Higher Weil Peterson volumes, and this was the first paper about it. So what's the setup? So we have our favorite moduli space of curves. Let's see, I need there is a seat free. This is good. I can use this because I need some place to put my papers. So what's the setup? So you have moduli space of curves, the universal curve, the projection down, and xi are your sections. And you take the relative dualizing sheaf, and I think many of you have seen these, so I felt it's okay if I write them down. Then you take you twist this by the sections to the power of a plus 1. So there's an a here. This a is the power here. You take the first term class, you push forward. So you get a class in h to a mgn with coefficients in q. So this a is this a. And so this is a nice form. So if you want to get numbers, you should integrate these things. So you should integrate over mgn bar. And now you have to get the right dimension. So what you can do is you can cap together enough of these forms so that the total degree you have is exactly the dimension of the moduli space 2g minus 3 plus n. And so if you think about this, so this has degree a, well actually there's a factor of 2. So this is a, and then I raise to another power of ma, so the total degree of this form is sum over a ma, which I call the norm of m underline. Okay, so what I have these forms of various degrees. It's just like Chern classes and Chern numbers, except that it's these, and these are these higher Weil Peterson volumes. Then what do? You write down a generating function Vg of this m. This is 1 over m factorial. This should be this, I think, m underline factorial. And then, yeah, that's right. And the product of the, so this is just a generating function, and there's a coefficient here. So the only thing are these combinatorial coefficients, but to go into depth on that one is not so interesting. And then we can write, for these, we can again write a generating function, and then the generating function here, and we've seen something like this already happen today. This has an x, and which takes care of the m, and then there's this s, which are the coupling constants for all the volumes. It's just a standard way of writing it. All right, so then what did we prove? So I'll write down the Einstein theorem, and then I'll point out what I wanted to point out. So what I want to get is, so this is part A. This is what I...
Correct, that it's really only a function of one variable, because if you take x and multiply it over to s and remove the first factor, it's a function of s, x.
You don't need x, but
Yeah,
it's fine. It's just to keep track of things. All right. Although there is something about the x which you will see here. So these are these are perturbation parameters, and that's the parameter of your one-dimensional theory. All right. So let me try to get to this point A. Yes, I can't. Right. So let me make the following definition. So to take k n1 and a, this is
Sorry, do you mind writing a little bit bigger?
okay, even bigger.
Yeah.
Then the formulas won't fit. All right, but I'll try. So this is a function of n1 to na. It's 1 over n1, n1 times n1 plus n2 times n1 plus n2 plus na. Delta A is a sequence, so these m's here, these form a sequence, and this is a sequence which has 1 exactly in A. And then what else do I want to write? So then there's something which I'm missing. Oh, there's. All right. So then here's a theorem, which was this recursion. It wasn't called topological, but anyway. So m a plus 1 times v m plus delta a. So that means in the sequence of m's, I increase the a's m by 1. This is equal to, and if it doesn't fit, it's because I'm writing so big. M bar is, oh no, I forgot a factor. So I partition my m bar into a plus 1 pieces. Okay, of n1 to na, product of the v mi, I equals 1 to a plus 1. And then, so I should say what?
Write sum of a equal to 1 to a plus 1.
Oh, this is I. I. Yes, I shouldn't write that because it's also wrong.
What's the definition? It means it says m bar plus a
Plus 1, yes.
What does that mean?
Oh, the n bar should be should get a norm. Sorry, the norm is some AMA. Okay, formulas are hard.
Underlying is a number, but its norm is not its norm.
Yeah, exactly. That's right. It's a sequence. And this is a weighted. So m is a sequence, and this is its weighted norm. It is its norm.
And without norm, it's just another number which has.
It's just another number. Without a norm, it's just a sequence.
No,
M1, M2, M3, M3, M4.
No, but you have this definition.
Yeah, but this is because these are sequences, and so I can add sequences. It's sequences in a semi-group, but actually, well, you can. Well, in the paper we write sequences in a semi-group, but our semi-group is n. So this is just pointwise addition. And where was I? I was explaining how the n1s and the n's are treated, and this is up to na. This is equal to, and this is the weird thing, m1 ma plus 2 comma 1 comma 1. Right, I start on the left hand side. I have the sequence m. This is fine. This is just subsequences, and these n's come from the m's by taking their norm. Should be underlines. And I add 2 to the first one and 1 to the rest. That's a formula. And then we do an example to see what's going on. So we will do this for the actual Weil Peterson volumes. Just look at V, M, and the rest are zeros. Let's call this Vm. So no underline. Then this says that m plus 1 Vm plus 1 is m plus 2 All right. Long formula, but the most important part, which I find astonishing, with hindsight, the point is that m is m1 plus m2, that we know from just boundary divisors, but we're computing m plus 1. So we're not splitting up m plus 1, we're splitting up m1.
Yeah, because you have this denominators one.
Do you mean from here to here?
Yeah.
Then also because 1/2 1 plus 1. That's the one I think. I just copied that, so I think it was correct.
This one of them should be wrong. Yeah.
Maybe I forgot the k.
Yeah.
Yeah, the k is missing, right? So sorry, I should.
Maybe K.
Yeah, k is missing on this one here. There is a k missing. Right, but the important thing is that this goes is a splitting of m1 and m2 into m, where I'm computing the m plus 1th person. Okay, that's this reduction. I have one. I'll draw a picture in a second. So that's the important thing, and then you can, from this you can get a differential equation. So you look at the generating function, and then you get something, again, what we've seen today, this morning, is if you look at, so I wrote the generating function f here, and now you'll see why I need the x, so it's this shifting differential function. So you get the differential equation that d by dsa of f is d by dx of the sum of k equals 0 to a minus 1 to the k f to the 2k plus 1 over, where am I, d by dx f to the k plus 1. I think I have that formula right. Times d by d sa minus k f. And you said d0 is x d by dx. Or the S0. All right, so again, I don't want to dwell on this too long, but the point is you get this, you have this recursion. This recursion has here this delta 1, so I have an extra 1 here. I split up the sum, and if I just do it into two parts, you see the two parts, m1, m2, they add up to m, which is subadditive with this m plus 1. That's why you get a recursion, and then you can rewrite that as a differential equation. That's the, and then these things become easier if you do a Laplace transform. Okay. So now this was part A, and now part B is how does this work with cohomological field theories? So now we have this 1B logarithmic 1D cohomological field theories. And yeah, maybe I'll do it this way. So what's the point? So if I have a 1D cohomological field theory, what you need are, so let's stick to genus equals 0, which is easier. So what you then need, you need the in of delta 0 tensor n in, so this is a sequence of cohomology classes in M0 n bar, and their Sn. This is also a point which is important, which I'll dwell on a little bit later, and we've seen this here a lot of times. These things are Sn invariant. All right? So that's what a 1D cohomological field theory is. Delta 0 is the basis element of your 1D space. Right? I mean, so your vector, your H is, no, it's an X. Your Hilbert space is C delta 0. And that has its coordinate x. So you have these in, and let's call this guy Cn, in of delta 0 tensor n. And you need that phi 0, phi sigma star of Cn is Cn 1 plus 1 tensor Cn 2 plus 1. So what is this? This is m sigma boundary divisor going to m0 n. So, and it's the things which look like this. So you have two curves here. So this is isomorphic to m n1 plus 1 bar cross m n2 plus 1 bar. And so this is your phi sigma. And let me also do the dual curve for this. So basically I have I and j here, and I'm separating them. The norm of I is n1, the norm of j is n2, and I have this s and t, which are the flags that I glue together. So this is different. This is the usual way you add up stuff. It's what happened on the right-hand side of my formula. So that's this thing, and then we can see that, you know, all right, we write Cn as sum over the Cn I, where the C and I live in H2I of the space, then if C3 0 is not equal to 0, this is called invertible. Maybe invertible is defined to be C, and normalized if the C3 0 is 1. And then we can take a log. Then we call lambda n is log Cn. And yeah, well, obviously Cn is x of n, x of this lambda n. And then the nice thing is the lambda n are primitive in a sense. Namely phi sigma star of these lambdas now. Lambda n, this is lambda n1 plus 1 tensor 1 plus 1 tensor sorry, lambda n2 plus 1. Okay, so and then there's a nice theorem. So how do these things connect? It's basically if I
This is logarithmic if you want, because this notion of logarithmic quantum.
no, it's not that. No, it's not nothing to do with it. It's your name actually. What was? It's in it's in this paper. Yeah, that's right. I also had to look at the paper again just to see what was going on. Anyway, so that's just because it's a logarithm, but it's important, I think, for this nice thing, and that's why you get something nice about the logarithmic coordinates, because they behave in this way. And then we also get this phase space. We call that large phase space back when. So what's the link here? So the link between A and B is the following thing. We can take we can look at omega of m and sigma to be the integral over the m bar sigma. So this was that guy of the pullback of our omega n m bar over m factorial. And then from this actually we get, let's see, do I have this? Where I write this? Yes, here. So from this we can look at the following things. So basically then we can take the Cn to be equal. So those are the same Cn's as here, the sequence of the Cn's. We can take those of the large Cn's. These are the integrals. So basically we can take the small. So we can take the, what am I saying? No, I'm messing something up. Yeah, I want these to be the boundary strata, but in principle I'm integrating something. So let me basically the Cn, which are the integral over the m. So it should be the large Cn, which are the integral about the m0n of the small Cn. And if we set the large Cn to be these integrals over these omegas, then omega, what did I call them? Omega n 0n. Then we see that we get this theory corresponding to. Sorry, actually I messed up. Did I write this out? Sorry, so let me just see what I wrote here. Oh, sorry, this is the first step, but that's not the correct formula. The correct formula is this. I want In is x of the sum a equals 1 to infinity SA omega n of A. So as I said, the SA just become coupling constants for the omega n of A. The omega n of A are defined here, so I take those things, those are classes. The IGNs should be classes in here, and then this is this one. And sorry, this one you can forget. I mean, this is not wrong, but let me take a shortcut and not define this. So I can define a one-dimensional cohomological field theory in this way. And this is actually a family with these SAs. And then the theorem says, so there's a theorem which is in KMK, the SA give coordinates to the invertible, the 1D invertible cohomological field theories. So they give you a basis, so these things generate. And I won't go into the proof, but the proof has something, I'll just write Y. This is something about the psi classes. This is something about the push forward of the psi classes. So this push forward of psi classes under this Pn and it's plus the self-intersection formula. So there is some geometry here why this works. There is some geometry, and I'll get back to that. All right, so that concludes part 1. And let's see, till when do I have? I always get confused in these things.
4:30.
4:30, so that's good. All right, so any questions so far? Maybe I'll go over it again. So what did I have? In the first part I showed I had this thing that I have this recursion which is of topological recursion type, and in the second type I had this feature that this pulls it back nicely to the boundary divisors multiplicatively, and if I take the log primitively. And then these two things fit together by pairing and the fact that we have these psi classes. So this is of course, then the thing that I erased is of course then if you want to have these INs and get numbers, then you have to integrate them, and that's the pairing between the forms that I have here and the cycles which are represented by the boundary divisors of the moduli space of curves. And then maybe I should add one more thing. So there's a follow-up paper by Manin and Zagier. And they add there's one more thing for, because you know these boundary divisors and you also know these boundary divisors, right? G plus 1n, so you have a double point like this, and then if you pull back these classes with this map, let me just call that phi. Then phi star of this lambda n plus 2, this is just g n plus 2, this is lambda g n, g plus 1 n. And then usually if you look at the topological recursion, you'll have one term for the n1 plus n2, which goes down by 1, and one term for the one which has a loop. Right, there are two terms. We saw this morning. All right, so this is end of part 1. So now I want to do part 2. And maybe I'll skip that. Yeah, that's a fun comment, so actually I'll keep that around. So let me see how did I write this down. So part 2, Hopf algebras. So this is one of the Kontsevich products. So let me write this out. Sum over in which one? Gamma tensor. Gamma 1. So let's look at graphs, and we've seen actually stuff like this happening already. I'll show you in a second that we've seen this happening already. So this is just a coproduct. Say I have some category of graphs. I look at the z-span, the free abelian group. I define a coproduct delta of a graph is the sum of all subgraphs in gamma, and then the quotient graphs gamma in gamma 0. So you consider the point is that the better point of view is that it looks like this. There is some actually, these graphs are morphisms. And I won't tell you what the objects are because I have finite type, but if this is a morphism here, I have a morphism here and a morphism here. And so basically what happens is that this delta here actually, so more generally, we're looking at, if I have a category, so let's say I have a category C, and I write the following thing, phi 0, and now I messed it up, didn't I? So now I have phi 1 here. Phi 1 tensor phi 0, which I didn't want, but anyway. So this phi is phi 1 after phi 0. So say this is finite condition. Decomposition finite.
What are the objects in this second interpretation?
The objects for these things are just the vertices. The vertices of the graph.
All right.
Okay, so here I should say the objects are vertices.
So it's oriented graphs?
No, not necessarily. But this is a very good point. If I get to point 3, this is a very highly difficult point with the orientation, and it also has something to do with the ABCD. But let me try to finish this in a second. So basically, let me get a few theorems and then give you some examples that you know.
Makes little sense to consider isomorphism plus of graphs, and consider this isomorphisms of arrows in some category.
Right.
And how vertices could be object of this category, because it depends on the choice of graph. It makes really no sense here. You have all graph. Objects are what? You have some category.
I have some category. Let me finish this and then show you what exactly the example is. So there's a definition which I don't want to write down too much. So well, let's look at the following thing. Let's look so F. So let's look at the monoidal category. And at the moment this is not symmetric. And then F tensor, I'm not going to give you this definition, is a Feynman category. If it satisfies some axioms. A list of axioms. And now let B be equal to the morphisms Z morphisms of F, and let F be decomposition finite. And the theorem is B is a bi-algebra with delta and mu equals tensor. And then, which is more important for the purposes here, there's a symmetric case. So now this F sigma is a symmetric monoidal category. But then you have to be a little bit careful. So B is basically the isoclasses of the morphisms. Z isoclass of morphisms. So maybe that was your comment of C, and then again B is a bi-algebra. And moreover, so plus some extra conditions. So let me write this as a statement.
So what's C here?
Sorry, wait, before you erase that, just say again what's that thing that you're erasing? Like, what was the statement supposed to be there?
There is no statement. This was a graph.
But what,
It was a motivation.
there was something about you have a category with objects.
No, there was no statement. There was a motivation. I'll make a statement, but this is was there a C? So there should be no C. Oh, morphisms of F. Yes, that's sorry.
Yeah, yeah. That's good.
It's a bi-algebra, and then if certain conditions are met,
But the thing that you just erased was supposed to hint to us what this co-product is.
right? Hint,
Okay.
underline, hint.
You're going to tell us more?
Yes, if I have the time. So if the more conditions are met, I, which is the ideal generated by id unit, it's a tensor category, minus id x, is a bi-ideal, and b mod h is mod I h, which is b mod I, is a Hopf algebra. Time check, yeah, I can do that. So example, so that let's look at the following category. G objects are corollas, are aggregates of corollas. So it's vertices, so they look like this: S1, SK. A corolla is a one vertex graph. I can do this as explicit as you want, but then I'll lose my thing. So what's this? The star S. This is one vertex, and S labeled flags.
So if your graph is kind of half edges.
Exactly. It's a.
Because it wasn't possible to guess.
No. Nobody said that. Nobody said that. So these are the objects, and then these form our. There is a category of graphs.
Right, S labeled flag of what? A flag of subspaces in some vector space?
No, flags. Half edges.
A flag of, oh, I see.
Line graph,
Yeah.
There is a category of graphs due to Kontsevich Manin. I can take the full subcategory generated by this, and then my F is a full subcategory generated by this. That doesn't say too much, but that's a valid definition. So now I can go back to my hint, which is in a sense much better than this definition. So what does a morphism look like? So, and what a morphism looks like, again, due to sort of time constraints, I won't tell you because there is a lot of combinatorial data that goes into this. But actually, this category is brilliant. It handles all the combinatorial data you want. So one of the things is you always ask yourself, what's the automorphism group of this thing? How many elements? One or two? Two. Exactly. Write your favorite definition of graph. Usually you come up with one. With this definition, you come up with two. Okay, so what's the? Let me draw a picture. So here's a picture of a typical morphism. I, J, S, T, I, S, T, J, I, disjoint union, J. Okay, so a typical morphism is a graph whose vertices are the source vertex, and if I contract all graphs, I get the target vertex. Another one is like this. I have S1 and S2, and I have S1, S2, I. And now I'm having too much fun. I think I have to be careful with the time. Okay, It's just a loop graph. I added a loop. Okay. So, and you can figure out these are actually primitive elements in the Hopf algebra. And those are the terms that sort of also appear in these recursions in a sense. Not quite. By adding a genus, so these are the pullbacks. So if I know the pullbacks to the pullbacks to the different divisors, these are the two things, and those are the two things that appear, and I can single them out in this Hopf algebra business as the primitive elements. And so we see that the logarithmic field theories, they behave nicely as primitive elements as these things do. Okay? Alright, so then there's a matter of genus, so then there's something that I kind of want to say. So, okay, so you can look at all graphs, but you can also just look at the graphs which are connected. And it needs to go lower. I may even have time to say this. I have till half, yeah, I have time to say this. G connected, then I can look at the things that are trees, so these are trees. And this is connected. And then there's a morphism here. And then there's a nice construction. There's a Grothendieck construction. And this I don't want to explain too much. I'll say what is correct. This needs to go lower. So this is the category where I look at graphs, but I want them sort of to be connected. This is the one that just has trees. There's an inclusion here. Same objects. Wide subcategories. Then there is something which I can't fully explain, but there is a natural construction where if you have a functor from this category, so it's a Grothendieck type construction. So remember, this takes some C and some functor from O. This takes some, it takes my F and a functor from O, from F to some category C. Let's say in this case it's actually set. It's easy. And then if I have such a thing, I can construct a new category. This is this category. I'll say this in a second. And I can construct a category here by push forward and pull back. So what is the point here? So I'll use O as T as the trivial functor, and O is the associative from F cyclic to set. So and the functors are easy, so I just give them on objects. So the trivial functor on star S, this is just a point, and the associative functor on the star S, this is a set of cyclic orders. Of S. So those two functors. Let me continue here. And now I can just tell you that somehow from this kind of picture, which is incredible. So if you take this K star, K shriek of W of the trivial and evaluate it at some point G S1 SB. This is homotopy equivalent to M G S1 SB. This is the actually there's another S here. Yeah, so the thing is that the points come with a cyclic order. That's exactly what happens. So I have to go up here if I want to do the bordered case. And this is kind of nice. So I can actually construct the whole moduli space. What that says is that all these things that I did previously, fooling around with the moduli space and talking about the Weil Peterson modules, I can do this. And this is a nice cubical complex, actually. It's a cubical complex. So this was this work with Clemens Berger. So we can do that. So this constructs. So it looks like we're just playing around with combinatorial data. The only thing I said that was it looks like I'm playing category games with set theoretic categories, combinatorial data, but that's not quite right. The W construction is a cofibrant replacement, and this is not the crowd for model category structures, but it's a cofibrant replacement in topological the topological category, and I'm taking my combinatorial structure to be a discrete set, but. Doesn't matter. So at the end of the day, so I have these two nice operators. I have these, they're primitive here, and they work here. So this is this bit there, and then what I said they're primitive, but this is exactly the whole point, was that if I have, if I have, maybe I don't have time for that. So you can think about what happens if I have a higher. Well, this is just one thing. So if I have a higher dimensional boundary divisor, this is given by some graph, and I can break it down into contracting one either an edge or a loop. And these are the two last things. But then if I know how to do that and pull back with the primitive element, I can pull back with all the elements. And by the way, primitive elements give you a Lie algebra, and I have a distinct feeling that this has something to do with this Lie algebra business. But this is part 3. So part 3 was, I didn't say this. So if you play this game, so this is if you play this game, if you take a category, which is easier. So here the Feynman category just has objects, the natural numbers, and you write them as n 0 n, so you could also think about a simplex. And you just look at surjections. Order preserving surjections. Then the formula you get out after the actually plus what's called Joyal duality. So it's a little more complicated than I make it out to be. But basically I could have a much simpler category than all these graphs. Just take surjections and play the same game. And then if I dualize once, then I get these things with overlaps. I get this formula, and that's the formula of Goncharov's coproduct for the multi-zeta values. And if you, so here, it's the same thing. If you want to do polylogs, it doesn't matter. It's also okay. Multi-zetas, the I1, I2 are just 0, 1, and for polylogs, you take points in C. So this sort of has these two features, and now I can do Weil speculation. So this is all proven. It's nothing speculative about this, but there's something which is interesting. So now I have sort of two sides. I sort of have this log side. Let me just call log homological field theory. So I have these pullbacks, and basically, and this is primitive. And actually the sigma here is also primitive. Right? Because the sigma was the boundary divisor or the other divisor, and the things appear as primitive. This is exactly this m1, n1 plus 1, and n2 plus 1. And n1 plus n2 is n. And then I have this side, which is sort of the topological recursion side, where the things look a little different, and I actually have them here. Because I was giving the talk to the preview to Maxim, so what happens in the topological recursion, I still have my two primitive elements, namely, but they look slightly different. What happens is the two terms in the topological recursion, which correspond to these two terms. So what are the primitive elements here? This is this guy and this guy. And what do they correspond to here? There is a correspondence. There are these things here, where this is just gamma and gamma thing, but somehow there is something new here. There is this extra root. Okay, and now I'll make a few remarks. So first of all, there is something called a B plus operator. So this is Kontsevich B plus operator. If you have something that is directed and has a root, so what I can take is I can take this gadget and apply it to gamma 1, gamma 2, and this is, just by definition, is you plug these two things, gamma 1, gamma 2, into here. So that exists. And now my handwriting is degenerating. So those are these two things. And so you can ask yourself, so it's like question 1, when do you have a B plus operator? Well, you have this in Kontsevich renormalization. And in this Feynman category business, you have that if your Feynman category F is actually the plus construction of some S bar. There is something called a plus construction. Okay, and now this is sort of Q2, and this is very important, is where did the direction come from? And I was rushing here, so actually I answered a question here which wasn't posed. I should have had G goes to G plus 1. I didn't have that in my graphs, but I could naturally get that. I do not even have to add that by hand. This is handled by the formalism. It's actually, that is an incredible statement in itself. This fact that just from pure combinatorics and push forward and Kahn extensions, you can get that G goes to G plus 1. Of course I can get it with surfaces, but it just comes from formalism. So the question is, where did the direction come from? And there is no direction here. And I think we also see that in this ABC D thing, because we saw it this morning. The point was, well, if I had, what's the difference? I mean, let me, as I said, this is part 3, so I'm freely, I'll write this here. This is disclaimer, this is 3. So I'm freely just saying stuff. So the point is, what's the difference between this, and so on. So this is, I think, I just learned this. This is B, and this is C. Let me not get into A. There's actually also A. It's directions, right? And previously, if I just look at dual graphs to curves, I don't have any directions. And it's kind of funny, because, and how did this work in topological recursion in the first place? There it worked because I didn't care. I had Sn invariants, and I could pick my first one, and it didn't matter, and then I had to sum over everyone. So this is, so I have to make stuff equivariant, and I choose one, so I choose the direction, and then the formula is equivariant with respect to that. But that is actually the same thing as looking at pullbacks and push forwards. This is taking, push forwards, turn stuff into co-invariants. So this is, so it must come from sort of some diagram like this, and we do know, what is happening here is, what should be happening here is there is a directed version of these things, and now I think maybe I'm only talking to 3 or 4 members of the audience, but there is a thing called props. And so there's a Feynman category for props that maps to the Feynman category for modular operads, which is this guy, which has these surfaces with genus marking. And so I can, and this has directions. This has directions. So I can push forward and pull back along this inclusion. And then, but then I should have had a B plus thing. So this is actually, it turns out this is very complicated. This is M plus. So this is my student Michael Monaco. There is a generalized plus construction for not only Feynman categories, but where you start with just an arbitrary monoidal category, and you prove a plus construction, and you go here. And then I think now you can match these two sides, that the B plus operators come from this fact that you added direction, which comes from this prop. Then you can write down things like this, which have a B plus operator. So you can cut these off. That gives you that side. And then the question is, which is kind of an interesting question, which I can't tell you right now, is why do these pair so nicely? So in part one, I said this is A to B, and the fact that they paired nicely there was the fact that the psi classes satisfy some nice relations on the push forward. And that is also actually where the direction came in. Because what happens is I have my moduli space, so there should be a pairing again, pairing between the two sides. And that's actually what this topological recursion should be about. And so the left hand, and then what I was saying is in part one, remember I had this A goes to B where I was looking at the push forward of these psi classes. But what is the thing though? Because the point is that this universal curve, 0, 0, n, this is m0, n plus 1. And this P, sorry. So the Pn star, what does it do? This forgets, so there is a special point here. So the magic that happened was I introduced the direction. If you look at the formula, so that's what I proved in my thesis, so I remember this. You remember that forever. So you pick an extra point, n plus 1, and then you forget that point. Now you see, but if I pick an extra point, I have a direction. At least on the tree it's clear. So for the other things it's a little less clear, but you can believe that. So I have a direction, I can work with that, and then I forget it, and then the formalism tells me that the rest is Sn equivariant. So it doesn't matter. So I don't see these things. So this one I cannot do. So this is like the rest is I just laid out. The rest is pretty much clear. So this is all true. That works out, so I can write these down. Actually, also that's why I'm playing possible sequel, because now you could do this for something simpler like the polylogs. I was wondering if because we had some topological recursion for other things than just volumes, and those could be the polylogs. Okay, maybe I won't say anything about the master equation. So let me just say this. If you want to ask me, there is something. So what is not here is part 4. And this would be fun with M02. Right? Or actually, in that sense, that's not very good, but I mean, we could look at T02, which is basically S1. And I think there's some things I could say about I'd say one thing. So if you look at the master equation doesn't work for the linear Mumford compactification. It works for the Kimura-Stashev-Voronov compactification. What happened there is that you blew up your double points to S1s. That's this S1. And I think that has something to do with this integral kernel that you have for the spectral curve. Anyway, I'll continue with that. So maybe I'll just stop here. Thanks.
Any possible questions? Comments?
I have just a small question. Is there a relationship between this Kronheimer Hopf algebra that appears in your talk and the Chen Hopf algebras of iterated intervals?
Yeah, that's exactly. So I raised the formula. That is exactly the point. Okay. That this formula, the one with this where I had I and then the repeated indices, that actually just says that these are Chen iterated integrals. If you go back to Goncharov's work, more or less all the relations that follow are because they're Chen iterated integrals.
So you can maybe use some of this to calculate periods of motives?
I mean that's what Brown and Goncharov do. Right, and then the Lie algebra structure actually appears there as well, because Brown takes the infinitesimal part of the Hopf algebra, and that's a co-Lie algebra, but that's just a derivation.
I see.
And then he uses those, and to prove Hoffman's generation result, he used exactly this. So it's exactly that type of thing.
I see. This is in which paper?
is well, his ICM talk and Brown's ICM talk, and if you check the one that I just said that was Carrillo, there's a reference in there to maybe it's the one in Annals where this is it, but I can show you.
Okay, thank you.
Any other question? If not, let's thank our speaker again.